uh, esteemed member of our community at the Mars Society.
Okay, great. Well, thank you. Thank you, everybody. Glad to be here. Let me see if I can get my screen shared. Share window. What window is this? Not this window. That's not a useful screen to share. Allow to share screen. Oh, come on. How do I share? Am I sharing now?
No, you're not. We saw something briefly, but then you stopped sharing.
Okay.
I think on Zoom you have the option to share your whole screen or just one window
Yeah, I
sometimes.
should. It usually works on Zoom. Now I'm not. No, it's not doing anything. Is this, how is that? Is that sharing now?
No, we do not see anything.
Okay. Oh man, I hate Zoom. Let's see. Yeah, NASA does not like Zoom back 5 years ago.
Yes.
All of the Zoom servers were in China, and that was
Yes.
unacceptable for NASA apparently. And now,
Yes.
and ever since they said, no, everybody else in the government is allowed to use Zoom without restrictions, but it's tricky. But okay, why won't this share? This is never, it's not been a problem before. Why doesn't it share now?
What are you seeing right now?
I am seeing a black screen that says James Burke.
Do you see the share button at the bottom of that still?
Yeah.
So go ahead
When
and
I
click
give it,
on.
it says share window or share screen.
I'd say share screen, and then you can alt tab over or switch windows over.
I've done that, and it shows nothing useful. Oh, wait a second. There's a little.
There we go.
Yeah, there's a little
Something's
pop-up
happening
button.
now. Cool.
Yeah. Okay, what's happening? Okay, how does that look? Is this shared?
It's still loading on my end. Does anyone else see anything?
It's still loading on my end as well.
Yeah.
Yeah, this is the worst Zoom sharing I've seen so far.
Yeah, it just says Geoffrey Landis has started screen sharing and it's spinning. I've never seen that before on Zoom. I would say stop sharing and try it again.
Can he send it to you, James, and you can share it?
Maybe.
I'm on my phone.
Let me instead go back. Try. Let's see. I just wonder if. Loaded. I'm sharing screen.
Maybe look for that pop up again because we don't see anything yet.
Share screen. What is this one? Show all windows. Okay. Okay. Anything going on now?
Yes. Now we see your PowerPoint looks like exploring Mars from rovers to. Yeah, this is good.
Okay. So apparently reloading did it. Okay.
Reloading did it. We're looking good now. We see your presentation full screen now.
Yeah, sorry. Okay. So what I wanted to talk about is basically sort of a little bit of experience with rovers and with in situ resource utilization. Let me look at my clock here, see how much time I have. So I just wanted to start a little bit about myself. I started out as a experimental solid state physicist working on solar cells. So my original background coming out of graduate school was in solar power. Then, of course, when I started as a postdoc at NASA, I switched over to solar power for space. And then one of the early projects I was given was the effect of space environments on solar panels. And the first environment that we looked at was Mars, asking the question, can we use solar panels on Mars? Now, remember, this was at the end of the 1980s when we had never sent a solar-powered mission to Mars, but we did a lot of calculations based on the assumed properties of dust in the Martian atmosphere, and we came up with curves that look like this. This is the amount of solar power coming to Mars as a function of time. You can see it rising and setting, and even with the dusty atmosphere, we calculated, yes, we can run solar power on Mars. So we made some of these curves, we sent them to NASA headquarters, and we sent a curve just like this, comparing Mars to Washington, D.C., which we figured NASA headquarters would understand, and told them, yes, we can send a solar-powered mission to Mars. And here it is, the Pathfinder and Sojourner, the first solar-powered mission to Mars. And I'd love to talk about some of my experiences with Pathfinder and Sojourner, but I only have half an hour, so I think I'll sort of skip on to some future missions to Mars. Pathfinder was successful enough that uh, the then administrator of NASA, Dan Golden, said, okay, we will send 2 missions to Mars every launch opportunity. These will be fast, frequent, and cheap. Well, okay. This would be the Mars Surveyor program. The first of them would be the Surveyor 98. The second one would be Mars Surveyor 2001. They would all be built on identical platforms. They'd be basically putting out missions essentially on a cookie cutter schedule. Well, hold that thought for a moment. Let's talk about in situ resource utilization, or ISRU. I'll use that acronym a lot. Everybody nowadays understands that in situ resource utilization is really the key to future going out, exploring not just Mars, but going out into the solar system. We need to start not shipping everything from the Earth, but using stuff that we can make. Well, what do you need to make? What do you need most? Well, by mass, you mostly need rocket propellant. You can talk about other things, but wow. The one thing that you absolutely need everywhere in space is propellant. And by mass, rocket propellant is mostly oxygen. So engineers, unfortunately, are risk averse. And I understand that. I've spent half of my life with advanced concept development and half of my life working on missions. And working on missions, when you say, I want to use this great new technology, the engineers always say, yes, I love that technology. That will be great, but don't fly it on my mission. I want somebody else to fly it first. So how do we start small? Well, what do we need most? We need oxygen. So back in about 1997, Dave Kaplan said, we need to do a technology demonstration to demonstrate making oxygen on Mars. He said, nothing but an actual demonstration on Mars, not on the Earth, would break that roadblock of the engineers saying, not on my mission. So that was a project called Mars In Situ Propellant Precursor. Well, okay, we know we want to use in situ propellant we make on Mars, but what propellant and how do we make it? Well, the Martian atmosphere is available everywhere. We don't have to pick a particular place on Mars. We don't have to dig down. If we land on Mars, we've got the Martian atmosphere, and that Martian atmosphere is 72.5% oxygen by weight. There's a number of different methods that have been proposed to make oxygen from carbon dioxide. So you've probably all heard about the Sabatier process, or possibly the reverse water gas shift process, several other processes that make methane and oxygen from hydrogen and carbon dioxide. We could bring hydrogen from Earth. We could produce it by electrolyzing ice. A different process is to simply electrolyze carbon dioxide. All of you who have had a high school chemistry class know you can electrolyze water, hydrogen oxide. You can do the same thing with carbon dioxide. You can electrolyze it and produce oxygen. So we picked that one. Why did we pick that one? Because it is simple and it doesn't need to dig down into Mars to get water. It doesn't need to bring hydrogen from Earth. We simply pump the atmosphere, electrolyze it, we can make oxygen. Well, easily said, it's a little bit tricky to do. This is how we do it. We do it with something called solid oxide electrolysis. So unlike electrolyzing water, where your electrolyte is in fact the water itself, here we use a substance called zirconia. It's a crystal. Interesting thing about zirconia is that it's permeable to oxygen ions. So oxygen ions flow through zirconia the same way, for example, hydrogen and hydroxide ions can flow through water. The bad news about this is you have to heat it up to about 750 degrees C to do that electrolysis. That's a pretty high furnace, but once you do it, you can make this oxygen from solid oxide electrolysis with this very thin membrane of zirconia. And also not mentioned, you need a catalyst to do the breaking up of the carbon dioxide. So, and there's just a picture of a much younger version of me with the hardware we made for the Mars in situ propellant production precursor. And there's the flight hardware. We built it. It was going to demonstrate that you could make oxygen on Mars. It's about the size of a shoebox. And it was great. We made the flight hardware. We delivered it. It was ready for integration in the spacecraft to fly on the 2001 Mars Surveyor lander. There it is. There's our ride to Mars. So we were ready. We had our hardware ready to go. And the first mission of this sequence crashed. That was the Mars Surveyor lander. The very first one was the Mars Polar lander. It entered the Mars atmosphere, was never heard from again. So our lander was identical. It was already made, identical except for the solar arrays. They put us on hold. A review board, an accident review board said faster, better, cheaper, needs a lot more work. So the program was canceled. So sorry about that. It wasn't even our fault. It was somebody else's spacecraft crashed on Mars and we didn't get to go. Turns out that was a bad year for a spacecraft on Mars. Everybody's spacecraft crashed. The Russian spacecraft crashed in '96. The Beagle lander crashed in 2000. The Nozomi space crashed. What else? Mars Climate Orbiter crashed. Yeah, somebody was shooting us down. In fact, at that time, if we did a listing of all of the spacecraft ever sent to orbit and land on Mars, turns out 2 out of 3 of them failed. Bad work. So what did we do? We decided to send 2 next time. And this time we sent them to opposite sides of the planet. So whoever was shooting them down would have to shoot both directions to get them both. And that was the Mars exploration rovers. I was part of this team, mostly working on solar energy and dust and atmospheric science on Mars. That was the Spirit rover, and then a month later, the Opportunity rover. And fortunately, both of them worked. There's one of the early pictures. This is a mosaic from the camera looking down on my nice, clean, beautiful solar arrays. Actually, the Mars Pathfinder led to the Mars exploration rovers, Spirit and Opportunity. They did great work. They were designed to last for 90 Martian days, 90 sols. They ended up lasting about 14 years for the Opportunity rover. Did some amazing science. This picture is looking at those little bitty blue dots. We called them blueberries. They're actually not blue. They're blue because the color is stretched. The scientists already know that Mars is mostly red, so they stretch all the other colors so they're bluer than the average Martian soil. And these were deposited from water. Another thing that we saw, a lot of the atmospheric team looked at this. We saw dust devils. And those turned out to be very handy for our solar-powered mission, because pretty much every day that we saw dust devils, we also saw dust being cleared away from my nice dusty solar panels. So that's one of the secret reasons that we lasted for 14 years of our 90-day mission, is that Mars was helping us out by blowing the dust off of the solar panel. So I showed you the picture from a couple of days after landing. Here's a picture from a couple of years after landing. We did get a little bit dusty, but if we could just hang on to the summer when the dust devils come, we would get the dust cleared off of the rovers. Well, every good thing ends. Here's the last image we got from the Mars rover. This one was never officially released by NASA, but eventually, even with the dust devils in 14 years, the rover mission came to an end. But not all of the rover missions, because guess what? We had a successor. So here's the family of Mars rovers. There's the little Sojourner rover. That's about the size of a Cocker Spaniel, maybe as big as your ordinary microwave oven. Off to the left, you can see the basically the test article for the Spirit and Opportunity rover. But then over to the right, you can see the Curiosity and Perseverance rovers. They're big rovers. They weigh about a ton. They're about the size of a small car. So they had a much nicer camera for doing self-portraits. So there's a beautiful self-portrait. This particular one is the Curiosity rover. You can see it roving on Mars. Another rover that did some absolutely magnificent work. Just a couple of shots of sort of these dry lake beds. And here we can see some of the cross-bed layers that show this is sedimentary rock that was laid down in a stream bed. But I wanted to talk a little bit, in fact, about in situ resource utilization on Mars. And we finally got to fly the Mars in situ resource utilization experiment. The MIT team picked up the idea. We worked them with a little bit on the 2001 rover. They took the idea and said, we're going to fly it on the Mars 2020 rover, the successor to Curiosity, the Perseverance rover. And there you can see buried right in the middle of that rover, sort of surrounded by all the science instruments, is this experiment called MOXIE, Mars In Situ Resource Utilization experiment. So it was designed to do just what we had tried to do with MIP. It would demonstrate the production of oxygen by that solid oxide electrolysis. Here's what it looks like. All of the little pieces sort of starting in on the left. Mars gas comes in, we compress it, we condense out the CO2, and then we put it through the solid oxide electrolyzer, SOXY, and that produces the oxygen, which we then measure and take it. I say we, but of course, this was the MIT team that did that. So it took us 20 years to get to Mars, but we finally sent the demonstration unit to make oxygen on Mars. It weighed 17.1 kilograms. That's a little bit heavier than your average shoebox, 500 watts, but it could produce up to 10 grams of oxygen per hour. And I guess really what we should say is it worked. There it is. It's sort of the gold-colored experiment being lowered into the rover. We flew it to Mars, and in 2021, it produced 5.37 grams of oxygen the first time it was turned on. And later runs, we increased it to the design specification, 10 grams of oxygen in an hour. So what can we do? Well, like I said, Dave Kaplan's original statement was we have to start small and work to larger applications. So what's the next thing to do? Could we use this ISRU oxygen to do a sample return mission from Mars? Launch it with empty fuel tanks and then make the fuel on Mars. Well, we're only making the oxygen using the MOXIE type technique. So can we use the oxygen to fuel a rocket? Here was our system design study. We land an ISRU oxygen plant. We have some big solar arrays because, of course, the way in situ resource utilization works for making propellant is we're taking energy, we're fixing that energy in the form of the oxygen. So we need a lot of energy to run to make oxygen. So that's the size of the solar array that we need. We did a lot of calculations on what can we use. We decided that we're going to use a hybrid rocket engine. This is one where liquid oxygen is the oxidizer, but we use basically a form of plastic for the fuel. There's an optimum mixture of oxygen to fuel. We decided to run it a little bit higher on oxygen because we were making the oxygen on Mars, whereas we had to ship the fuel from Earth, and ran some of these performance curves for both ideal and actually experimental versions of the fuel production. So the study on that showed that just 1 or 2 stage Mars ascent vehicle could use in situ generated oxygen using the same technology as MOXIE that was already demonstrated to launch our 5-kilogram sample capsule into orbit. And this is better performance than using the mission without the in situ propellant. So this really shows that we could use the ISRU. It would pave the way for human exploration and also accomplish real science. But turns out they didn't choose it for the NASA sample return mission. Sorry about that. They thought it was too complicated. So we got sidelined once again. And actually, at the moment, it looks like the sample return mission is almost certainly going to be canceled. We're not bringing samples home from Mars anytime in the near future. That's that part, partly about engineers being risk averse, but mostly it's about, man, that turns out to be an expensive mission. So I think I'm right about on my time schedule of half an hour. Just a quick conclusion is that use of resources in space is critical, absolutely critical to expanding into the solar system. The Moon and Mars both have resources that we can use to start with oxygen and rocket fuel. In the future, everything we need to live, work, and explore can be done with in situ propellant production. And with that, maybe I'll switch back to unshare and ask for questions.
Okay, Dr. Landis, thank you so very much, and thank you for being patient at the beginning. We have Julian would like to know, are we allowed to take inspiration from the MOXIE? Yes, I can answer that. Yes, you can use anything that's already invented, you can use as an inspired piece of equipment. So I'll take that answer for the contest. And Karun says, how many grams of oxygen does the average human require per hour? You are going to have to research that on your own. That's part of your study. Do you think another way to generate oxygen on Mars as an alternative is to build massive greenhouses with plants to generate oxygen, or would that be too slow?
In the long term, we're going to have to use greenhouses on Mars to generate oxygen simply because we're going to send people to Mars. We're going to want those people to live there long term. And obviously, we can't keep shipping food up from the Earth. So yeah, greenhouses on Mars is a great idea. It should be doable, but it would take, if we want to generate rocket fuel, which we need in quantities of tons, yeah, probably a chemical method is going to be better. It takes an awful lot of trees to generate tons of oxygen. Of course, on Earth, we have trees. We have trillions of trees, not to mention algae and other plants. But on Mars, well, do the calculation if you want, but I think
Right.
when you do it, you'll find out you're probably going to want more oxygen than a reasonable amount of trees would provide.
I agree. You'll have to have both eventually. And the next question is about discovering carbon-based or silicon-based life. Yes, it is possible. I'll just answer that quickly. Yes, that is possible somewhere in our solar system or universe. Dana said, what are the most promising improvements in solar cell technology that could make solar cells more efficient for use in a space mission? That's a great question.
Yeah, solar cells technology has been improving rapidly, and the best solar cells we use in space are almost twice as efficient as the ones that are typically used on Earth. The next step that people are looking at is primarily in space to put more junctions on the solar cell. So if we split the solar spectrum into more pieces, we can use each piece of the spectrum more efficiently. With that said, though, the interesting big direction with solar cells is how to get this very, very high efficiency at a lower cost. Solar cells in space are hundreds of dollars per watt. Solar cells that you buy on the Earth are less than $1 a watt. So what we want to do is get that very, very high efficiency, but make it for low cost. And then once we do that, we want to re-import that technology back to space so that we now have low cost solar cells for space. A lot of people are looking at the question of, well, once you do that, can you start making the solar cells from materials you find in space? That's another application of in situ resource utilization. Pretty much all of the planets and moons we talk about have rocks that are made of oxides of silica. So in principle, it's possible to make silicon in space. Also, some of the other materials we're talking about for solar cells are actually very, very, very thin layers, often thinner than a coat of paint. So if we can just make the substrate that we put the solar cells on, we could make solar cells in space. So that's another direction that we're looking at for the future of solar cells.
Wonderful. The next question is about the difference between going to moon and Mars. That's a question for another professional.
No, I work on Mars and the moon, so
Okay.
we look at them both.
Well, I just mean in this situation, they're just trying to compare which one's going to go first, etc. I think they're both going to happen. It's just a matter of time. Do you agree, Dr. Landis?
Yeah, I'm actually fully in line with the current NASA thinking, which is the moon is a stepping stone to Mars. The moon's a 3-day trip. Mars is at least a 100-day trip and probably more like a 180-day trip. So it makes sense to try out all of the space technologies on the short trip before getting ready for the long trip. Makes sense to me.
And then do you think we can develop improvements to autonomously clear solar panels of dust? Great question. Efficiently.
Yes, I think we can do that. It was another one of these things where the engineers say, oh, yes, I love it. We should do that, but not on this mission. We did an analysis of the dust effect on the Mars exploration rovers. We gave it to the engineers, and the engineers said, okay, no problem. We'll just make bigger solar arrays so that even when they're dusty, they'll keep working. Well, okay, that was the engineering solution, just make bigger solar arrays. That turned out to be very handy for the mission because it gave us a lot of extra power, especially early in the mission. With that said, clearing solar arrays on Mars is a little harder than you'd think. If you just take a brush and brush across the solar arrays, saying, I'll just brush the dust off. Well, if you've ever tried walking across a carpet on a very, very dry winter day, you build up static charge. Mars is a very cold, very dry environment, and it's easy to build up static charge. So you have to be sure that whatever you rub against the solar arrays is more efficient at removing dust than it is at building up charge that would attract more dust. These days, we're mostly looking at electromagnetic methods of removing dust. Just sort of put a moving charge on it and try to clear it off with electrostatic dust removal.
Wonderful. Next question, and then I'll get to the hands raised until our next speaker arrives. Ishan says, I would like to ask, is solar energy the only way to power rovers, or are there a better way to power them?
Yes, the two choices for power systems in space are either solar power or some form of nuclear power. And when we talk about nuclear power on Earth, we mostly think of nuclear reactors, which are pretty big and heavy, but put out massive amounts of power. In space, we usually use radioisotope thermoelectric generators, or in the next generation, radioisotope Stirling generators. And these can be made in the hundreds or possibly potentially in the future, thousands of watt power sources. When we moved to the Curiosity and Perseverance rovers, they put in these nuclear power sources, the radioisotope power sources, instead of the solar panels. That really gives them night and day operation and allows them to not worry nearly as much about dust. So they're the two options. Solar arrays are certainly lightweight. That's the great advantage. But the farther you get from the sun and the less solar energy you get, the more the nuclear options start looking good. Especially, for example, if you're going to the permanently shadowed regions on the moon. Well, for those, nuclear options would look good. For human missions in the long term, you might want to do an actual nuclear reactor, a power plant that does uranium fission and produces power.
Wonderful. And Sham, there's several hands raised. We will answer questions until our next speaker arrives. Sham Bu Saad.
Hi, Dr. Nicole. Hi, Dr. Geoffrey. I'm Sham Busad from Syria, Saraya Smart School. And my question is, all the focus currently is on discovering carbon-based life. It's possible that there are other life forms. Space missions have not focused on some important possibilities for silicon-based life forms, for example.
Yes, I agree that if we discover life elsewhere in the solar system, it's very possible it won't be life as we know it, but something completely different. And that, of course, would be the absolute best case scenario because we would learn so much if we could find a different type of life that's completely different from Earth life. There's a lot of arguments in the space community about whether it's even possible to make silicon-based life. So that is a completely unknown question. We don't know the answer to that. The problem with looking for life as we don't know it, types of life that we don't know about today, is that we don't even know what to look for. We know what the signatures of our type of life is. We can look for proteins, we can look for chirality, we could even look for things like DNA and RNA, but we don't know what other types of life might look like, and it could be very different. So beyond that, I can tell you if you talk to astrobiologists about this question, they will tell you that there's a lot of debate about what we look for and how we look for it.
Great question. The next, Jad Yassin, please. Go ahead.
Good afternoon, ma'am. Good afternoon, Professor, and thanks for the great presentation today. I'm Jad Yassin from Syria, from Saraya Smart School team. But I have a small question about as a NASA scientist, what is the future ways to provide oxygen for the habitable rovers that can astronauts in it breathe correctly and have enough quantity of oxygen?
Yeah, I think ultimately, very similar to MOXIE, the way to produce oxygen for breathing in the short term is electrochemical techniques that split the oxygen off of carbon dioxide. In the long term, however, as was mentioned earlier, I think for humans, we're going to want to make greenhouses. The reason is that greenhouses produce not only the oxygen from the exhaled carbon dioxide, but also will produce the food that you need. So you need both food and oxygen for support of humans. So we're going to have to use greenhouses on Mars, on the moon, and elsewhere in the solar system.
Okay, I believe Joseph is here. Joseph Palmowski, you are in the room, correct?
Yes, I'm here. Can you hear me okay?
Yes, perfect. Thank you so much, Dr. Landis. Feel free if you would like to stay on and answer some questions in the chat. Joe Palmowski will now be joining us.
Okay, well, thank you for inviting me.
It is my pleasure, and this will be posted on YouTube. And students, I would like to welcome our next speaker, Joe Palmowski. Please welcome him, and he will be speaking of RedWater. I'm very interested in this presentation, and I'm sure the students are too. Thank you so much for being here.
Yeah, of course. I'm happy to be here. So yeah, can you see my slides okay?
Yep, perfect.
All right, thank you. Yeah, so Joey Palmowski. I work for Honeybee Robotics. I'm a systems engineer. I've been with the company for about 7 years now. Started as a mechanical engineer, kind of channeled into more of like a project lead role, and now sort of evolving into systems engineering. Just a little bit about the company. So we were founded in 1983, but we're actually now fully owned by Blue Origin, which is Jeff Bezos' space company. So it's kind of cool. We get to work alongside the folks building the rockets that will take our stuff to space one day. So yeah, we are part of Blue Origin now. We have 400 employees across Honeybee's 2 locations. We have a location in Altadena, California, which is in the Los Angeles area. And then we have a location in Longmont, Colorado, which is in the Denver area. I'm affiliated with the Altadena, California location, which is our exploration technologies group. We specialize in robotic systems for space exploration. So we build systems for the moon, Mars, Titan, and even Earth as well. Just to highlight some of the projects we've worked on. So you can see the drill down here in the corner. That's our Trident drill. So that's a drill designed for the moon that recently flew on Intuitive Machines' second lander to the moon. We also have other flight payloads for the moon that recently were successfully demonstrated on the Firefly Blue Ghost mission. One of those I'll talk about here in a little bit. Back in the early 2000s, we built the rock abrasion tool for Spirit and Opportunity rovers on Mars, which was essentially a grinding tool to prepare the surface on Mars for those rovers to take samples, or excuse me, to analyze the rock on Mars. And then CB21 rover is our latest announced effort. So we're actually going to be a rover company now too, which is cool. And then I mentioned Titan, so New Frontiers mission, Dragonfly. We built the drill and the sampling system for that, which should be flying, I believe, in 2028. I feel like if you're here, you probably already understand ISRU fairly well, but I'll just go over it really quick. So in situ resource utilization, in this case, we're talking about using the available resources on Mars instead of bringing them with you from Earth. And when we're talking about Mars, at least in the near term, the primary consideration is given to the CO2 in the atmosphere, which is about 95% composition, and then water ice, which is more recently believed to be even in the mid-latitudes of Mars and potentially very large quantities. Yes, you can have subsurface ice deposits, like I mentioned, and those can be anywhere between 50% to maybe even nearly pure ice. If you go deep enough, it's believed maybe around 10 meters in some of these prime locations is where you'd start to see ice deposits. And then you have your surface hydrated minerals, which could be processed for 8 to 12% water content, and those should exist in the top meter. So the primary usage, the bulk majority of these resources would initially be used towards rocket propellant manufacturing, but there's also obvious usage for life support if you're talking about humans on Mars. And why are we talking about doing ISRU? So this is not my graphic. Jerry Sanders, who's kind of a sort of a legend in the ISRU world, has talked a lot about this, where you pay a massive penalty for taking these resources with you from Earth to Mars. So 226 kilograms on Earth would become 1 kilogram of propellant on Mars. So it's pretty obvious that we want to explore the options of these resources that already exist on Mars. I'm going to go over this particular ISRU mission architecture that's sort of based around Honeybee's RedWater system, which is what will be the primary focus of this talk. So assuming the water is being extracted via the RedWater system, we'd need to collect, and we're just kind of baselining Starship because they seem like, the people actually the closest to potentially doing this thing. And just to say, just to add, Starship is on the much larger side of a MAV that would leave the surface of Mars. So that would be about 600 tons of water would be required for processing to turn that into rocket propellant. Now that, again, that's on the high side. So there's been other architectures proposed with smaller MAVs that might be more on the order of 150 to 200 tons of water. But still, you need a lot of water. As far as how do you power this system and the other systems related, that's still very TBD. I believe you've heard other talks on that, so I won't get into detail, but nuclear power feels like the eventual solution that makes this more of a robust, scalable concept. You just heard about MOXIE, so for CO2 capture, something like that would likely supplement a RedWater system for the CO2 capture. And then you'd have your production plant that would actually be doing the conversion from water to methane and O2. So talking a little bit more about the subsurface ice on Mars, which is the actual form of water that we would leverage with a RedWater system. There's been a lot of work done in this area more recently too, analyzing data from different Mars orbiter data sets that we've received over the years, and it seems like there's sort of a convergence among a few locations. Arcadia Planitia is thrown around a lot. I believe Elon Musk in his most recent talk, he kind of name dropped Arcadia as where they would plan to set up shop. So that's a popular one, but basically the criteria here is obviously you want to have all the indications that you potentially have large quantities of water ice below the surface. And of course, this is not anything 100% certain. Additional data sets would help constrain it a little better. The resolution of the data isn't great, and it was intended to be more of a something that would look for deeper below the surface. So it's hard to constrain it beyond or any closer than 10 meters at this point with any confidence. But then you also don't want this location to be far away from where everything else has to happen for entry, descent, and landing, and where you would actually want humans to settle. As far as the actual technique, so if the ice is presumably under up to 10 meters of overburden, one option is, of course, you could cut the ice out and try to bring it to the surface, but that's a pretty energy intensive, complicated endeavor. So what we've done instead is sort of run with this idea that's been proposed. Dr. Stephen Hoffman, I know, did a lot of work within the past few years to work out this architecture where you actually leverage a Rodwell. So a Rodwell is not necessarily a new thing. It was proposed, I believe, in the 60s by the US Army for remote locations on Earth in the Arctic and the Antarctic, where it can be very expensive to bring in water, which you're obviously going to need in large quantities at certain military establishments. So they proposed drilling into the glacial ice, introducing form of heat to build an underground reservoir of water, and then you can recirculate and do heat exchange at the surface, and then draw out water as it's needed from the well. And by doing this, you can create a fairly large scale source of water in very remote locations. So that's the concept that RedWater builds upon. And so you can kind of see this kind of cartoonish graphic of what would maybe be more of a demonstration. There's no mobility, so if it was on a lander, wherever you land is where you're going to drill. Ideally, you'd have more constrained information on where exactly these ice deposits are, but you're kind of looking at the base, like the minimum system that you're going to need to demonstrate this technology. I'm going to talk a little more about the specifics of the mechanical systems. The CT storage drum, CT stands for coiled tubing. You're going to have your gas storage, so gas is used to actually excavate cuttings from the hole. Water, you're going to extract the water that will eventually have to be relocated to a processing plant. You'll have some sort of cuttings deflector, so you don't want when you're doing this pneumatics excavation, you don't want your cuttings coming back and hitting your lander, so you want to sort of organize your cuttings at the surface and potentially use those as well, right? Those are still a potentially good resource. And then down in the subsurface, so the packer here is, so on Mars, you're right at the triple point of water. So if you expose the water to the Mars atmosphere, will technically sublimate, may not happen quickly, but it will happen. And then sort of twofold, if you have this packer, you can pressurize downhole, and there's some positive benefits you can get from that as well. So that's essentially an inflatable membrane. So which you can essentially seal off around the borehole that you've drilled. And then you'd have your actual Rodwell where you'd introduce your heat and start forming that. So the ConOps would be, ideally you'd have some form of mobility instead of a lander. You would find that location that, there's subsurface ice. You do your pneumatic drilling process. You release gas in order to blow cuttings out of the hole. Once you've passed this rocky overburden, so you're using a rotary percussive drilling technique, so you can break rock and remove what's needed. You want to go, once you reach ice, sort of want to continue through ice to create a little bit of additional overburden, so you're not melting the ice right above you and potentially collapsing your hole on top of you. So once you've reached this depth, you can go ahead and seal your packer, introduce a small microenvironment in that hole, and then start priming your well with downhole heat. If you have the ability to pump the water to and from the surface, you can then create even more effective heat transfer by returning the water to the surface, heating it, putting it back. And then this creates this sort of recirculating process of growing your well. And then you can, so the current version of this system, we actually, instead of pumping, which pumping on Mars, especially at great depths, can be extremely difficult, especially if you need to put a pump down into the hole. So right now we've sort of baselined a system where we can actually utilize the gas that we already have to create positive pressure to push the cuttings out of the, push the water out of the hole. So that's kind of what you see in the final ConOps here. And the packer allows you to create that positive pressure in the downhole cavity. A little bit more about Rodwell. So the Rodwell has been well modeled for the terrestrial use case, but we of course wanted to consider that for Mars too. So we put in some work to try and understand understand how this well would grow, just to kind of constrain a little better what we expect our energy consumption, our peak power, our efficiency to be based on a given payload volume. So 43 megawatt hours, it's quite significant, but this is to acquire 100 tons of water. So I'll come back to it later, but as I said, 600 tons is sort of your magic number for a Starship refill. 18 kilowatts peak power, so sort of right on the boundary, I believe, of what a large solar system could potentially do, and not extremely efficient. But when you compare that to the alternatives, it starts to look better. And there's ways that we can potentially tweak this ConOps and how we grow the well to improve upon that efficiency. But that is a tough one, just given the thaw radius of the ice and sort of how your heat is not going to stay within that well. You're going to have losses into the surrounding ice as well. So there's still room for improvement on that. Right now, just baselining essentially a 300 kilogram payload, just looking at the RedWater system itself in order to produce this 100-ton well. So just briefly to talk about other concepts for deep drilling on Mars that we've explored. So a wireline drill, this is commonly used in the ice drilling industry on Earth. And we won NASA funding with JPL to develop a system that would be for a science objective. So JPL built this Watson spectrometer that we attached to a robotic drilling system that could drill deep into the subsurface and do analysis, for instance, for search for life on Mars would be a potential use case. So this system works really well for ice, but it does require, because you're using an umbilical cable and not a rigid tube, you have to generate your weight on bit downhole. So in order to press into the formation while you drill, you have to have some sort of additional mechanism to grip the borehole wall and push yourself down. So it adds complexity. And the umbilical cable itself is not as good of a strength member as like a rigid tube would be, so that could potentially be a single point failure. So the technology is potentially good. It's also more difficult for when you have this rocky overburden. It's not ideal for that. So it's more likely suited for Mars polar activities where you expect ice right at the surface, or Europa or other ocean world exploration. And the advantage is you can go much deeper than coiled tubing, on the order of hundreds of meters potentially. And we did actually test this system in an analog at Greenland Summit Station, and we reached 110 meter depth. So we know the wireline system is potentially a good option for certain types of mission architecture, but most likely not this mid-latitude subsurface ice application. So that brings me to coiled tubing. This is something that's been around since the 60s and potentially earlier. It's widely used in oil and gas, and they have large systems that can potentially go up to thousands of meters deep. It's essentially a long continuous steel or stainless steel tube that you pre-bend or coil along a drum or a reel, and then you use what's called an injector to mechanically grip and push that tube downwards, creating your weight on bit, straightening the tube, and using it to penetrate the subsurface. One of the advantages is because you have this steel tube that becomes a natural protective conduit for anything you want to put down hole, including electrical wires, pneumatics, and different fluid lines as well that you'll need for the RedWater architecture. One of the really cool things is we've actually already demonstrated this technology on the moon, which is arguably just as hard, if not harder, environment to test in. This was one of the payloads I was talking about that was on Firefly's Blue Ghost mission. There are, so I'll talk a little more about Lister here in a second. The few drawbacks: this injector requires a very large amount of torque. So if you don't want to be too power intensive, it could potentially be a much slower process to penetrate the subsurface. And then at some point you're limited to your depth because your tube will buckle, since that's what you're using to generate that weight on bit. I'm gonna skip this overview of Lister, but I do want to show the video of the actual operations on the moon, which is really cool. So this is using coiled tubing, but a much smaller system. So this is only a 1/4 inch diameter steel tube, and they're using pneumatic gas as well to jet the cuttings out of the surface. So this was about a month or two ago we completed these operations, and overall it was very successful. We got to about a meter deep using this system, and unfortunately the characteristics of the subsurface were much more like a gravel rock formation than we were expecting the lunar regolith to be. We were expecting more of a powderized system. So where we had the capability of going 3 meters, we went 1 meter. So one of the advantages to the RedWater design is with Lister, it was just a pneumatic probe, so it didn't drill. So on RedWater, we have the ability to rotate and percuss, so we can actually break up larger formations like gravel and rock and turn that into a pulverized dust before we pneumatically clear it out of the hole. So just a quick bit about the development progress of RedWater. This is a project that was funded by NASA's Next Step 2 funding, Appendix D for ISRU development, research and development, and initially had this phase 1 effort where we designed, did a little bit of trade studies initially on, and then designed and breadboard a system in order to test some of the critical subsystems that still needed to be confirmed. So this system is essentially taking the coiled tubing concept from oil and gas, but it's significantly miniaturizing the system into a very small footprint, as opposed to being something that would be mounted on like a large truck. This is something that you could lift potentially with, lift it off the ground with your hands. So it's quite scale reduction that we had to figure out each of these subsystems for. And then we demonstrated this system in freezer and TVAC testing as well. This is the video we have of growing a, I want to say like a six liter well, maybe a little larger than that. And so we were just basically validating the ability to use this robotic system to create the Rodwell. And then we actually had a leak in our ice block, so we weren't able to pressurize down below to pump it out. But so that was unfortunate, but we just about fully demonstrated the entire end-to-end ConOps of this. And then we moved into our phase 2 of this funded effort, where we advanced the technology to a NASA TRL-6. So you can see where we went from something sort of modular that we could turn knobs and adjust the system until we liked the output of it. We went with something that would more resembles the Lister for the moon, sort of locking in all this. So we also took a lot of lessons learned from the previous phase. So the sealing material did not work so well in the Mars-like environment. So we adapted that to something similar to Mars Pathfinder airbags. So use that heritage to redesign the packer. And then we also had some thermal issues where you get some melt and refreeze action that could actually get your drill stuck. So we added some heaters to the system so we could melt ourselves out if necessary. And built this end-to-end system and tested this one just in freezer this time, just given the time and funding that we had at this point of development. But that was an overall success as well. So that's where we've left things with this effort. So I just briefly wanted to touch on some of the information that was just released by SpaceX or in Elon's talk about Elon Musk's talk about their Starship architecture. And I always take this with a grain of salt. So there's always like a safety factor when it comes to the dates that he'll say. I typically say 1 to 2 years longer at least. So when looking at this sort of timeline that they recently presented, we're probably in this, when we actually need to be flying something like a RedWater, that's not just a tech demonstration, that's actually mining for resources and generating propellant for a return mission. That's the early 2030s, probably more closer to, the 2033, where this last one would be, is probably more likely, but that's not very long to build a complex system like this, beyond just sort of the lab and TVAC testing that we've done. And then when we're actually looking at, what is it, how does this translate to Starship refuels, the system that we currently baseline, without getting too in the weeds, the system, it's very difficult to design the system that would be, something on the scale of a 600-ton well to produce for a Starship. It may be possible, but looking at what we've at this stage baseline, I mean, we would need basically 8 of these to produce. I have 600 versus 8, so obviously probably more like 6 or 7 of these, but that kind of gives you a little bit of a safety factor there. And so you're to build 8 RedWaters is a pretty significant endeavor for a 2033 timeline, but I would like to think we're about as far along as you'll see any technology that's proposing to do something utilizing the ice deposits in this part of Mars. So it's definitely possible, and then potentially additional development efforts will lend to a system that can scale more, and also maybe potentially a retractable system. So in this sense, it can be difficult to try and reuse the tubing that you've deployed. In the oil and gas system, they kind of take advantage of having a large footprint where they their coil diameters don't have to be as large, but because we're fighting against volume and mass constraints as well, we've really had to condense this coil diameter, which means sort of a limited fatigue life on repeating, you know, the deploy and retraction of the steel tubing. So still some design challenges there, but you know, for a smaller scale system, it just comes to like scaling up the quantity of systems you have to provide. And yeah, that's it. I'm more than happy to answer any questions that anyone has.
Wonderful presentation. There are some questions in the chat. Oh, Jeff's answered some of them. Okay. Thank you very much, Dr. Landis. 2 questions from Laksh. Given that water is essential for life support and fuel production, what unexpected challenges did you encounter in ensuring the purity and potability of the extracted water, and how does your system guarantee it's safe for a human colony? That's the first part.
Absolutely great question. Not a great answer of the black box. So a lot of Honeybee's focus has been on the mining component to this. I think it's going to be a big like team effort. Different entities are going to be providing different subsystems to the overall architecture. Honeybee is at least not yet. Maybe Blue Origin will eventually get there, but we're not really. It's not our realm to sort of post-process the water. It could end up being the case, but as of now, we've been very focused on, you know, how do we physically access and extract this water? But it's going to be extremely important to have potable water for, you know, human life support as well. And I do think I think not long ago I saw a NIAC that was maybe in a phase 2 or something, proposing something like that. And we occasionally get, you know, people reach out and say like, we have this technology that we'd like to sort of baseline RedWater as giving us the water that we would purify. So that is absolutely being considered. It's just not a focus for Honeybee at this time.
Thank you for that answer. The second part of that question is, if I'm planning to expand my base, what's the most efficient way to scale up the water extraction using RedWater's technology without significantly increasing the energy footprint, which is crucial for long-term sustainability?
Yeah, I mean, something's got to give, right? You're fighting latent heat when it comes to melting ice. So you do have like a minimum amount of energy required just to melt ice. And at that point, it becomes like a knob you can turn with the efficiency, which we're learning can be very challenging. If you have the power, you know, you don't want to overcomplicate your system for a little bit of an efficiency gain. But I would think ways to potentially improve upon it is look at the Rodwell itself. How can we minimize the losses so you get this like sort of thaw radius in the ice? You could just picture like an outline of this Rodwell going X distance outside of it, which is where you get some sort of delta T until you finally have, you know, the in situ ice temperature. So all that heat going into the ice, if it's not melting the ice, it's considered a loss. You also have to fight convective heat transfer to the air around you, which is not going into heating that water and melting it. You don't want to overheat the water because ultimately you really just want to melt it. So you could definitely fine tune this system to continue to improve upon efficiency, which will in turn bring down the power and energy requirements of the system.
Thank you. Layla, would you like to ask your question? And this will be the last question via Zoom to be respectful of Joseph's time. The rest of the questions, if you'd like to send me via email, I will forward them if the scientists have time to answer.
Hello, thank you for this valuable information. My name is Layla from Syria, from the Saraya Smart School team. May I ask you a question? My information tells me that the surface of Mars isn't made up of tectonic plates like Earth, and that its interior is solid. Thus, earthquakes are unlikely to occur. Why then is there a seismometer on Mars? And if earthquakes are detected, what is their cause?
Definitely not my strong suit. As far as the potential risk to something like a RedWater system, I do think you know, it's calculated risk for sure. I don't know the scale of Mars quakes and what sort of impact that could potentially have on the you know, the structural integrity of a Rodwell. But it's something that probably needs to be considered. You know, the other thing we have to think about is borehole collapse. We get that question a lot, but we're always sort of very surprised to see the integrity of our borehole. So we've always proposed that we could add some sort of mesh to a borehole to provide the you know, the additional support required to avoid the borehole collapse. And you could probably imagine potentially have something with your Rodwell. But I think to some degree, if you lose one, you just take the loss and you do a new one. It's probably gonna. I think that's what we're gonna find on Mars is like there's always gonna be a trade of getting over complex and over designing a system for those sort of considerations versus just, you know, trying again and bringing more payload to Mars to do it.
Thank you, Layla, for that question. And I would encourage you to do some geological research as part of your science objective. And that may answer your question. Joseph and Geoffrey, thank you so very much for your time today. This will be uploaded to YouTube as soon as it comes down from the cloud. Students, you may rewatch it. I will put it in the syllabus. I will link it there for you to rewatch and share with your teammates if they missed today's presentation. Thank you, everyone. I will see you again on Tuesday. Please gather with your teams on your own between now and Monday to start planning and implementing your competition paperwork. Thank you so much, everyone. Have a wonderful day. Email me if you have any questions.
Thank you.
Thank you. Bye.
Thank you so much, Mrs. Nicole.
Thank you.
Thank you.
Thank you.
Thank you. Bye.